Hi everybody, Andy Walding from Cellstream and the Online School of Network Sciences. One of our most popular articles at the Cellstream website was an article that I wrote way back in 2010 on the address resolution protocol. We've seen over 240,000 people have read this article, and I hope it's helped a lot of people. I thought I would take that importance to everybody, and I turn this into a little video so that you can learn a little bit about what the ARP protocol is. So let's take a look at this. What is ARP? ARP stands for the Address Resolution Protocol. This protocol is used by network nodes, devices on your local area network, to match IPv4 addresses to MAC addresses. This allows us to fully communicate on the layered protocol model, which I'll talk about here in just a minute. The original specification for ARP was found in RFC 826, and that has been since updated by RFC 5227 and 5494. So that's where you can find some of the details on ARP from the specifications point of view. The protocol functionality is divided into two pieces. One piece determines exactly what the physical address is so that I can send a packet to the right destination on the local area network or beyond. The other part answers the requests from other machines. So every machine on the network has to be listening for ARP requests and then sending replies. And we'll look at this in a little bit more detail here in just a minute. Now, ARP is not used in IPv6 networks. It's only used in IPv4. Instead, in an IPv6 world, we use something called neighbor discovery, which is done over the ICMP v6 protocol. Now that's a whole nother subject, and we'll just sort of park that to the side. But if you're in a purely IPv6 environment, you're not going to see ARP messages if you try to capture them or try to see what's going on with the ARP protocol. All right, so what is the problem that ARP solves? Well, let's talk about this for a minute. So first of all, I'm sitting here, let's say, on my computer. And let's say I'm reading my email and I receive a coupon from a vendor and I say, ooh, I need to print that coupon so that I can use that the next time I go. All right, so I'm going to send or click on the print button right on my computer. So what my computer wants to do now is it now wants to send information across my local area network to my printer. Now that printer is configured in my system. I know what its IP address is. So I can say, yep, I know its IP, but I have no idea what the MAC address is of this printer. That information is not stored in your layer 3 routing table. It just knows about IP addresses. Now, why is this the case? This has to do with something called the order of operations. So let's talk about that for a minute. So the order of operations in your machine follows that layered protocol model, or think of it like a layered cake. Okay, so we have layer 1, layer 2, layer 3, and layer 4 and above. Okay, I'll just leave that as sort of one thing. Layer 1 is your physical layer. So this is where we transmit the actual bits. Layer 2 is your data link layer. And this is where we have the Ethernet protocol in most local area networks. Layer 3 is your network layer. And this is where we have the Internet protocol. And in our case, we're going to say IP version 4. Now, layer 4 is, TCP and UDP, and then, of course, all the applications. So remember, we wanted to print something. So if you think of the order of operations, we are going to travel down this protocol model. This means that I must know the IP address before I know the Ethernet address. And that is exactly what ARP is going to help us to solve. So what's going to happen here is we're going to send out to the network, we're going to basically broadcast this to everybody, and we're going to do an ARP request. And we're going to say, who has whatever the IP address is? Let's say it's 192.168.1.7. Let's just say that. So that's what this is. 68.1.7. So who has 192.168.1.7? Now, the printer should be listening for these ARP requests. And what it's going to do is it is going to send a reply. It's going to come back and it's going to say, you can find me, or you can find that address, at some MAC address. So let's just say it's MAC X, whatever that is. We'll see an actual demonstration of this here in just a minute. So that reply now comes back into the computer. And what happens here is this is placed into a cache. Okay? And now the computer continues its journey. Remember, it knew the IPv4, it now knows the Ethernet, so it can actually now transmit and send that printed document to the printer. Let's say a couple of minutes goes by and I print another email. That information is going to be in the cache, so I don't need to go and request again. I can just look at the cache and I can get an answer. So this is the overview of the problem that ARP solves. All right, so with that said, let's summarize, right? So ARP provides a method for hosts to send messages to destination addresses on a physical network. And basically what it's trying to do is it's trying to match the 32-bit IP version 4 address into the 48-bit Ethernet address. This is then placed in a cache, as we said. It's called the ARP cache. If the address is already known, so I already have sent something to the printer and the cache has not cleared and that entry has not left the cache, then basically I can proceed. I don't need to send any ARP messages. If I don't know where that device is, then I will send out this ARP request, and then the target machine, as we said, will answer. Now, ARPs are transparent to bridging. Basically what we're saying here is that Ethernet switches and bridges and so forth, they transmit these ARPs within the local area network. However, routers do not propagate these Ethernet broadcasts, and so ARPs do not go beyond the router, which is at the edge of your, let's say, home network or your business network. It may not even leave your local area network if you have multiple routers, if you have multiple subnets within your network. You're not going to see ARPs go across the routers. Okay, so very important to know that. So what does the protocol look like? This is a visual representation of the protocol. We have 32-bit words here, and then we have a byte counter down the left-hand side. So basically you could cut this into 8-bit bytes like this. So this is byte number 1, byte number 2, byte number 3, byte number 4, and then of course byte number 5 starts right there. So that's how you read these types of protocol diagrams. They exist in all of the standards. I've just turned it into nice pretty colors. All right, so what we see here is we have a hardware type field, we have a protocol type field, then we have a couple of length fields, followed by an operation. And this is where we will see whether it is a request or a reply. Then we see 4 very important fields. We see the sender address. Now this is hardware, so this is the MAC address of the sender. We see the sender's IP address. Then we see the target hardware address and the target IP address. So if you were doing a request, you would put your MAC address in here, your IP address in here, you would put the target IP address, like the printer, there, but this field, this target hardware address, would be all zeros, because you don't know what that is. That's how the request would go out. Now the reply would come back with all 4 fields properly filled out, and now that information can go into our ARP cache. Okay, so that's a sort of visual representation of it. Another way to look at it is through a tool like Wireshark. So I've dissected a couple of ARP messages here so we can see how Wireshark has represented the information within the protocol to us. Okay, in this first example, we're looking at packet number 86 right here, and we see that this is an ARP message. And Wireshark has done a great job here. It's basically translated the contents of this and says, who has 192.168.1.1? Please tell 192.168.1.153. Okay, so this 1.153 is the one that is actually sending out this message. We also see that this is broadcast, so this is going to be sent to everybody on the local area network for trying to resolve this IP address 192.168.1.1. Okay, so we can see the details of the protocol right here, and it matches that diagram that I had on the prior picture. So we see that it is hardware type, the protocol type, the hardware size and protocol size, and then we see that it is a request message right there. And we see the sender MAC, the sender IP, 1.153. We see the target MAC is all zeros. That's what we said is going to happen. And then, of course, the target IP address. So we're trying to find out who has 192.168.1.1. What is your MAC address? Now, it turns out that in this particular packet capture, that the very next packet, packet number 87, is an ARP response. Okay, so we see here that 192.168.1.1 is at that particular MAC address. And sure enough, here it is. We see address resolution protocol for Ethernet IPv4. There's the two sizes again. This time the opcode is a reply, and we can see all of the fields are fully populated. So it's saying to 1.153, this is 192.168.1.1, there is my MAC address, and of course it's confirming the MAC address of the requester. So we see the whole thing dissected for us here inside of Wireshark. Pretty cool. So what have we learned, right? If we turn this into just sort of a diagram, if that was all a little bit too busy for you, what's happened here is that a broadcast request was sent out, okay? And the destination MAC address of that was to everybody. And then we saw a reply. Okay. Now the reply is not broadcast, it's unicast. So the replies only go back to the original requester. And if we just step back here for a second, we can see that is the case. We see that right here is our broadcast message, and then we see that this was sent back unicast back to the original requester. So if I'm sitting on the network and I didn't send this request, I may see the request go out. Of course, it doesn't match my IP, so I'm not going to do anything with it, but I won't see the reply because the reply is being sent to whoever asked. So that's pretty cool, right? But it means that if I then want to connect to that same printer, it's a different machine, I want to connect to that printer, then I have to ARP the printer as well. All right, so pretty cool. Now there's a couple of special ARP messages. One is called a gratuitous ARP, and I've put the full definition here. But basically what this means is that there are ways to simply send out like an ARP request with a gratuitous reply. Okay, so it could mean that I'm just doing requests without really having any data, and it could mean that I'm a router simply sending out replies telling everybody that they can find me at this MAC address. And that's really helpful to help the network run a little better. So again, gratuitous ARP messages can exist. They might be identified, by the way, by Wireshark. There are two other types of ARP messages. There's the inverse ARP protocol, which is basically the opposite, right? What it does is it knows the layer 2 address, but it needs to know the layer 3. This was done in primarily ATM and frame relay networks, and for the most part, those don't exist very much anymore. So you can pretty much just, this is informational. However, reverse ARPs, which are very similar because, again, it means I don't know my layer 3, but I know my layer 2. So I'm filling in different fields. This can be used to actually obtain a layer 3 address. Now, today, reverse ARP is essentially obsolete. It was replaced by BootP and then, of course, DHCP. However, you might see this inside some virtualization environments where, you know, in the virtualization environment, you've set up what the IP address range should be, but you don't have a DHCP server. So if you're kind of wondering, how did those virtual machines boot up and how did they know what address to use? They probably did a reverse ARP, and the internal software of that virtualization environment provided an IP address to that machine. Again, you can see this if you capture inside those sorts of situations. All right. Now, there are 3 different exercises that we're going to do. I'll just give an overview to these, and then we'll provide each one of these in a separate video. The first thing I'm going to do is I'm going to show you how you can do ARPs on your own machine. Okay. In the second exercise, I'm actually going to create a virtual network, and then what we're going to do is we're going to go in and we're going to do a little experiment with this and see how ARP works in this little network experiment. And then lastly, the third exercise that we're going to do is we're going to see how we can use ARP to do discovery. Now, there are tools to do this, things like Colasoft and Nmap, and we will do a little bit of both of those things in the discovery portion. So let's do those next. I'll see you in the next video.